Alrighty, welcome to chapter 23. This is the first in 4 chapters on statistics and probability. I'll be honest with you up front, I don't love the IB's treatment of these topics. I think that AP Stats does a much better job of making probability and statistics come alive to you, the student, making it feel relevant in real life, because this is one of the most important, no, not one of, this is the most important topic of all of HL mathematics for the average human being. I'll put some links in the video description if you're interested in more about that. Also, to be frank, IB statistics is just lazy on a number of points. Some of those will come up in these 4 core chapters. Some of it doesn't pop up in a math setting unless you take the IB statistics option. But some of it also shows up in IB bio. Never accept the null hypothesis. Never. Anyway, this video is going to cover all of chapter 23. It might be a little on the long side. All right, let's do it. First off, a whole bunch of vocabulary from section A. The good news is that I don't really remember having to know the difference between most of these words ever for core stats question, but I mean, just to give you a little example here, if I were to go out and talk to a sampling of United States adults, right? So I'm going to take a survey of a sample. Maybe I find out something like their average height. That would be a statistic. If I were to talk to every single U.S. adult, I'd be taking a census of a population. Their average height would be a parameter. Unless I were to use that average height to describe the average height of adults on Earth, in which case it would be back to being a statistic. So context is really everything in the world of stats. That's one of the things that I love the most about stats, although it's also one of the things that quote-unquote traditional math people dislike about stats the most. There's a famous quotation, perhaps you've heard of it. It's often attributed to Mark Twain, but I'm not sure that he actually said it. The quote is that there are lies, there are damn lies, and then there are statistics. And I think there's definitely some truth to that. Anyhow, down below we've got some distributions, and we'll talk more about this later on. But I just wanted to point out this one here is called positively skewed. The bump I know is to the left, if it's which is in like the negative direction, but the name is the opposite of that for reasons we'll discuss later. And the one on the right is called negatively skewed. In the AP stats world, you may also hear of these as being skewed. This would be skewed right, and this would be skewed left. So that at least kind of matches the backwards names here. Negative is to the left. But it makes sense if you think about it, not in terms of where the hump is, but in terms of where the hump isn't. Outliers down at the bottom, that's a pretty important thing. We should know what an outlier is. For us, though, it's really just, it's a number that's much larger or smaller than the rest. We will not concern ourselves with calculating exactly what data is or is not an outlier. We're just going to kind of use the eye test. It'll be obvious to us if a number is an outlier. Don't worry about having to draw that distinction yourself. We're going to be dealing with numerical variables. Numerical variables could be of 2 types. The first is called a discrete variable, and that's going to be the result of counting. So discrete basically means that there's going to be gaps in between the values. Like if I was counting people in a car, there's either 1 person or 2 people or 3 people. Like there's no such thing as 1.5 people in the car. Continuous variables are a result of measuring, and there are no gaps in between them. It's kind of like a discrete function versus a continuous function, as you would have seen in calculus. We're not really going to be responsible for making graphs. I can't think of a single IB exam question where we had to make our own graph to display data, but we will need to be able to read them. So here up top, we've got a tally chart. There are, looks like there's 8 values of 1 in my data set. There are 9 values that are 2, 6 3s, 5 4s, and 2 5s. We can count up their frequency, which is really just a number as opposed to a tally. So these 2 columns are really saying the same thing. And then relative frequency is just the percentage of the total. So this is 8 out of 30. I guess that must be 26.7%. We can use column graphs or histograms to display data. Column graphs and histograms are essentially the same thing, except a column graph has gaps in between the bars. A histogram doesn't. A column graph is for discrete data. A histogram is for continuous data. Okay, so if I was counting up the number of matches in 30 match boxes, well, that sounds like discrete data, right? Like I can't have, I mean, I don't know, I guess if I broke a match in half, does that count as half a match? No, that doesn't count. We just don't count that one. So this is clearly going to be discrete data. Letter B, the heights of 25 hockey players, or the heights of whoever, it doesn't matter. That's going to be continuous data. Even though they say it's to the nearest centimeter, so that technically means we're rounding, and we can't have anything in between, say, 149 centimeters and 150. The measurement process is continuous, so I consider that to be so. I promise you we wouldn't have to draw any graphs, and I'm standing by that. This is just a textbook question, but here's what the graphs might have looked like, just so we can see. Here we have the various number of matches are along the x-axis, and then the height represents the frequency. Over here, we've got different categories. Our textbook calls these groupings classes. The calculator calls them bins. I just call them groups. Whatever you want to call them is fine by me. The first bar is representing heights of 120 to 129, because that's what the grouping is over here. The second one is 130 to 139, and so on. Do you have to do it this way? Do you have to have the bar not include the highest value that we see, but include the lowest one? No, we could have flipped this. We could have made this first bar maybe 121 to 130, and then the next one be 131 to 140. The groupings are totally arbitrary, but we just want to be consistent. Okay, interpreting a histogram. This is not an exact science. Letter A, how many of these seedlings are 400 millimeters or more in height? Well, 400's right here, so what number is that? Like I don't have the exact data in front of me, so I don't know. It's a little more than halfway between 8 and 16. So what do we call it? Like 14? I don't know. Yeah, maybe that can be 14 and this can be 6. So I'm going to say it's like around 20. If you're asked to interpret a histogram, there's not necessarily a right answer. But if you say some, ridiculous number, like, I don't know, there's 50 of them there. Like, no, it couldn't be 50. Obviously. So just pick something that makes sense. Okay, letter B. What percentage of the seedlings are between 349 and 400? So for that, we get estimates for all the bars. We add them all up. These two are the two that we're interested in. Those are the heights between 349 and 400. So that's a total of, what is that? That's going to be 60, that's going to be 70. Right, and that's 70 out of a total of 120. So whatever 7/12 is as a percentage seems like a decent enough answer for letter B. Letter C, so this was based on a sample, this whole graph here. We're told that the total number is 1462. So if we wanted to estimate how many were less than 400, well, the quickest way I think to do that is to say, all right, what's the percentage that were bigger than 400? I'm doing bigger because that's just fewer ones to add up. So that's going to be 20 out of 120, and that's at least, that's nice. That's only 1/6 are greater than 400. So that means that 5/6 should be less than 400. And then we're just going to work out 5/6 times 14. Well, not 1492. That's Christopher Columbus. 1462. And simplify that, and that'll tell you about how many seedlings are below 400 millimeters. If you wanted to add up these four and just go directly from there, of course you can. I don't know. I'm bad at adding, so I knew 14 plus 6 off the top of my head. I didn't want to have to deal with those four. And same thing for Roman numeral 2. That brings us to section B, which is about measuring the center of data. There's a few ways to do that. One thing you can try to do is measure the mode. Hopefully you've heard of the mode before. It's the most frequently occurring value in the data set. I have nothing else to add here. Maybe you'd use the mean. Very challenging stuff. I'm sure you know how to calculate the mean. Here it is written out in some more algebraic flair. This will be necessary to keep in mind to do some more advanced things later on. And the third measure of center is called the median, which is literally the middle value. Okay, And if there's an odd number of values in the set, then it's just the middle one. If there's an even number of values in the set, then we just take the average, the mean of the two that are in the middle. And one way to tell which one it is in a set is to use this formula right down here. If there's n numbers in the set, the median is always the n plus 1 over 2th data value. So the mean and the median are the two measures of center that we'll be most interested in this course. First, we'll look at symmetrical data sets. This is just two different images of what a symmetrical data set might look like, but there are other types. In any symmetrical data set, however, the mean and the median should be basically the same value. They're going to be very close in value to each other because, looking at this example on the left here, the median is going to be right there because there's roughly the same amount of data points to the right of it and to the left, which I guess is visually, we could think of that as like the same area to the left and to the right. And the mean is going to also be basically in the center there because there are no extreme values to the right or to the left to pull the mean in either direction. Most of the values are closer to the center, so the mean is going to stay there as well. A good way to think about the mean is that it's like the center of gravity of this distribution. If I were to try to like balance this thing on a little fulcrum, the mean would be where it would stay balanced, which is certainly in the center for this example, and also for the one on the right. It would stay balanced there. Again, there's some values that are farther away from the middle here, but they're balanced out by those on the left. So the mean is going to stay in the center, and the median also, because, again, it's the exact same area to the left and right. They're the same number of points to the left and to the right. We can compare this to a skewed distribution. Talked about this earlier. So on the left, we have the positively skewed or skewed right distribution, and on the left, we've got the, on the right, we have the skewed left or negatively skewed distribution. For those, their name comes from where the mean is with regards to the median. So if you look at that comparison, here the mean is farther to the right than the median. And I've tried to draw some more kind of extreme images down below to get the point across. The reason that the mean gets drawn towards this long extended tail out here is that that tail indicates that there are extreme values very far away from all the others. And that's going to affect the mean quite a lot. And it will not affect the median at all. Going back to heights, if I look at the average or just a list of all the heights of doesn't matter, a sample or an entire population. If I take the tallest person and I multiply their height by 1 trillion, that doesn't change the median height. The median height is still in the middle of the data set. Just because we have this one gargantuanly tall person all of a sudden doesn't change the median height. But the mean height would change quite a bit. So in a skewed distribution, the mean gets pulled towards the extreme values in the extended tail. The median stays further towards the center. I think before we move on, this is a good point to call your attention to the formula book, which has quite a lot going on for chapters 23 through 26. Chapter 23 concerns itself with this first box, but as you can see, there's still quite a bit yet to come within this unit. And I don't know, in my opinion, these are the most dense formulas in the entire formula book. Some of them are easy to use once you know what's going on, but there are a lot of symbols to interpret here. Some of them even have like calculus thrown in, like, whoa, what's going on? Don't panic, it's going to be okay. But yeah, in my experience, students tend to have the most difficulty with these formulas. I think because other formulas, it's much more obvious in a problem how to apply them. Whereas these, you have to really spend some time reading each one of these and understanding what each of the symbols really means, to then be able to apply it in the context of a problem that has like a lot of words and other stuff going on. So we're going to want to take our time with these. But as I said, we're just dealing with the first box for today. So let's read through these. Population parameters. Let n equal this. So n represents the number of individuals in a population. And this is just the sum, we've seen that before, of f sub I. So f sub I is just going to be, f in this case stands for frequency. So literally this is just saying if I add up the frequencies of whatever group number 1 is, so that'll be f sub 1, plus the frequencies of group 2, so that's f sub 2, and so on and so on and so on. If I add up all the frequencies of all the different groups that I have, that equals the total. And that should be obvious. Moving down below that, we have the mean, which we just saw a moment ago. We know that the mean is the sum of all the data points divided by the total number in the population. So we're dividing by n, that's obvious. And the reason that it's written out in sigma notation here is because rather than writing out x sub 1 plus x sub 2 plus x sub 3 and so on, sometimes data points are repeated. So writing f sub I times x sub I, that's going to tell us it's the frequency of whatever x sub 1 is, multiplied by x sub 1, plus the frequency of x sub 2 times x sub 2, and so on and so on. And think about that with numbers, right? Like if you had like 3 data points of 2, so you're adding up 2 plus 2 plus 2. That's the same thing as doing 3 times 2, right? That's all that this says. And down below we have variance and standard deviation, but we're going to talk about them in section C. So let's do some work with means for now. Okay, this problem is like the easiest thing in the world if you just know what all the symbols mean. So mu is going to be our symbol for the mean. But, you know, I didn't mention this earlier. Quick timeout. This is a Greek symbol mu. We're going to use that for mean throughout this course. If you're taking AP Stats, you might also be familiar with x bar. Wonderful. That also means the mean, but it's for a sample. For IB statistics, we will only be dealing with mean and standard deviation of a population. We're not going to do anything to do with a sample. So if you are using any outside textbooks or websites to look up statistics stuff, I need you to ignore anything that talks about samples. We're really doing all work with populations. This is especially important when we get up to standard deviations, as you'll see, because the formulas there are very different from each other and will give you different answers. So it's crucial that we choose the right one. Anyhow, back to this problem here. Mu, that's our average, that's 11.6. So I know that 11.6 is equal to this thing, that's the sum of all my data divided by how many data points there are, which is 10. Oh, so what is the sum equal to? It's equal to 116. So easy. Okay, so this problem. What the heck is netball? Don't worry about it. Actually, no, worry about it. Go Google it. It's an awesome, like basketball's cousin. Anyway, we know that this particular netballer, whatever that means, they played 14 matches and they've had an average of 16.5 goals per game. So 16.5 is equal to the sum of the first 14, the goals that they've scored in all of those first 14 games, divided by 14. So I can deduce from this that the sum of the first 14 games, they've scored a total of 231 in those first 14 games. This is really important because now we know that in the 15th and 16th games, she is throwing 21 and 24 for a grand total of, from 1 to 16, we've now got 276 goals, and then we can calculate their average by doing 276 by 16. Okay, something like this. We have a whole bunch of data values. We don't know what one of them is, but we know that the mean is 4, so we're just going to solve, this equation here. 4 is equal to the sum of those 9 data points divided by 9. Easy to do. So now the book finally gets around to formally introducing the formula as we saw it in the formula book. In the previous section, each data point was only appearing one time the way that we thought of the formula, so the frequency of each data point was 1, but that might not be true. So at the right, we have a frequency table. There's 1, 3 in the table, there's 1, 4, there's 3, 5, 7, 6s, and so on. There are a grand total of 40 data points represented here, and the sum of those 40 data points is 278. We can find the average, of course, by doing 278 divided by 40. And hopefully this illustrates to you why this formula here makes sense. Here we have some information given to us in a frequency table. We are asked to calculate the mode, median, and mean. The mode, very easy to calculate. Clearly 11. That's the value which the highest frequency. The median, also easy to calculate, slightly more challenging though. It's going to be 11. The median, remember, is the middle value. One way we could use the formula that was given to us earlier and do 30 plus 1 divided by 2, and that's going to give us 15.5. So it is the 15.5 data point. So really what that means is that the first 5 data points are 47. The next 4, so that takes me through data point number 9, are 48. And then I want to find data point 15.5. Clearly that's going to be one of those 1149s. And really, there's no need to use this formula. I mean, if you just know that you're looking for the middle value here, you know there's 30, like you can work out that you're looking for 15.5, right? And then you can go about it in this same way. Okay, so the median is 30, and now for the mean, we have to do a little bit more work. We're going to have to calculate 47 times 5, 48 times 4, 49 times 11, and so on. Add up those 6 numbers together and then divide it all by 30. What we're going to get is 1,471 divided by 30. When we do that calculation, we're going to get 49.0 to 3 sig figs. So the mean we could say is 49.0. Do these results support the company's claim? So they claimed that on average, there's 50 matches per box. Does this support it? No, it doesn't. We got an average of 49. It's close, but it's not 50. And if you think about this from the point of a consumer, like, I don't care if you're lying to me with how much you say the box has, if you're lying in the wrong direction. Like, if you're claiming there's 50, and then it turns out there's like 1,000 matches in the box, that's awesome. I just got bonus matches. But don't lie to me and give me fewer than you claim were there. Now, part C. This company ends up winning a case in court, claiming that they had false advertising. Why is that? Well, I mean, the sample size here is only 30 boxes. You know, maybe in a larger sample of, I don't know, 1,000 boxes or something like that, maybe we'd get a higher average. We could have just gotten unlucky here. So in general, the larger our sample size is, the better idea of the population parameter we'll be able to estimate. Okay, when the information is gathered in groups, or I told you the book uses the word classes, calculator says bins. So we don't know what the data points are. We can still get estimates of the mean and the median and the mode by just taking the midpoint of each interval. That's going to be our approach. Is this perfect? No, but it's as accurate as we can get. Okay, here we've got a frequency histogram, results of some exam, whatever. How many people sat for the test? Here, it's much easier to estimate the heights of those bars than in the last one we saw. Those are all multiples of 5, so that's cool. I add up all the red numbers, and I'm going to get 125 people. Estimating the mean score for the test. This is the most labor-intensive part of this question. So again, I don't know what the actual data points are in between 80 and 90. Or for any of these bars. So we're just going to take the midpoint. So the midpoint of the first bar is 85. I'm going to multiply that by 5 because that's the height of that bar. I'm going to add to that the midpoint times the height, plus the midpoint times the height, plus the midpoint times the height, all the way to the last one. That's 155 times 10. I'm going to divide that by all the people taking the test. That's 125. Calculate this out. I get 119. As far as the last 2 parts are really easy. What fraction of the people scored less than 100? Okay, less than 100 is just going to be these 3, so that's going to be 15 out of 125, or 3 out of 25. And then what percentage scored more than 130? So that's going to be these 3 together. That's going to be 35 out of 125. You can do that division. It comes out to be 28%. All right, now we're on to section C, talking about standard deviation, which is a measure of spread or dispersion, although I don't use that word. I'll talk about spread. This is important, right? Because at the right here we have 3 different graphs which all have the same mean. They all have the same median, in fact, because they're all symmetrical. But they're all spread out quite differently. And I think this is an important thing to take note of. In previous courses, you may have come across other measures of spread, such as range or interquartile range. I think you all know what the range is. This is not talking about all the possible y values of a function. No, this is, statistically speaking, range means the difference between the maximum data point and the minimum data point. So that's easy to work out. The interquartile range is the difference between the upper quartile, or sometimes called the third quartile, and the lower quartile, which is sometimes called the first quartile. If you don't know what those are, they're easy to figure out. What you do is here, this is a data set that we'll be looking at. So first I've arranged them from least to greatest, and we calculate the median. That's great, that's 6. And then we figure out the median of the set to the left of that value. So if I look at the median of these, we get 3. So 3 is going to be our first quartile. And if I look at the median of these, then we get 8. So 8 will be the third quartile. So 8 minus 3 is equal to 5. There's multiple ways to do this because in this case it was obvious there was only one data point in the middle there. What if there was an even amount there? What should you do then? Some people would say that you do what we did when calculating the median and you take the 2 data points in the middle. Other people would say, well, then you would include the original median in your calculation. There are different perspectives on what the right way to do this are. Or is, grammar, whatever. The point is, it doesn't matter, okay? You can calculate your first and third quartile really using any coherent and consistent mathematical technique, and this is true for AP Stats, and it's true here as well, especially because, as I've said a few times, I've never seen a question asking you to do this on the IB, but just in case, just know that there are different ways that you might see out there. It's all good. Just do something that makes sense. These statistics, the minimum, the maximum, the first quartile, the third quartile, and the median, which is also technically the second quartile, put together, they're called the 5-number summary of a data set, and they can be used to make something called a box plot, or sometimes called a box and whisker plot. So here's a box plot for the data from the previous page down below, and you can see the 5-number summary are the 5 important parts of this graph. I can calculate the interquartile range just by looking at the distance from one end of the box to the other. I can calculate the range by calculating this distance there. Well, I missed. You get the idea. A box plot, if it comes from relatively symmetric data, will be symmetric itself. If it comes from relatively skewed data, the box plot will also show that skew. Using the interquartile range, by the way, is one way to calculate what an outlier is. So take the IQR, multiply by 1.5, add that to the third quartile, or subtract it from the first quartile, and anything beyond those values is considered to be an outlier. This is not the only way that outliers are calculated. There's other methodologies that make use of the standard deviation. This is the one that I've used when teaching AP Stats. I think it's the easiest one to use. I know I'm repeating myself a lot here. I don't think you'll need to use this in IB Stats, but I just want to cover the basics for you in this video. And one last thing is percentiles, which our book is describing as the score which a certain percent of the data lies at or below. When I teach AP Stats, I just say below it. Again, this is something that different statisticians, different textbooks, different websites are going to have different definitions of, so it doesn't really matter. In fact, I mean, you can construct a data set in which what we're staring at here is obviously false. If I have a data set of just 3 values, okay, so the median is clearly 2. Does that mean that half of the data points fall at or below 2, or using my definition, below 2? No, that's clearly not true. But I think the spirit of this should be observed. The median is going to be, generally speaking, pretty close to the 50th percentile. The first quartile will be the 25th percentile. The upper quartile is going to be the 75th percentile. I think that should make sense. Which, just to tie it back to an image from earlier, so that would mean that in the box plot to the right, 25% of the data points fell between 1 and 2, 25 between 2 and 3, 25% of the data points between 3 and 4.5, and then 25 of the data points between 4.5 and 8. And you can kind of get that sense from this histogram up above as well. The fact that it's so skewed means that, yeah, we do have like 25% might be in that area, whereas 25% might also be there. You can see, one's higher, but one's wider. And one final thing, there's something called a cumulative frequency graph. Okay, there's a lot going on this page. Let's take it piece by piece. First, in the top left, we have whatever. There's some sort of competition, and the competitors finished within certain times. Maybe this is a marathon or something like that. So 8 people finished between 2 hours and 26 minutes and 2 hours and 28 minutes. 3 people finished between 2:28 and 2.5 hours, and so on. We've added to the right here a column called cumulative frequency, which is very simple to see what it is. It just means the frequency from the beginning up until that point. So the first 2 numbers are always the same. Okay, the second number here, 11, this is the amount of people finishing in between 2 hours and 26 minutes and 2 hours and 30 minutes. There's 11 of them because there were 8 in the first group plus 3, that gives us 11. This next number down here, 20, is the amount of people between 2:26 and 2:32. And you can see that's just this 11 plus this 9 gives us 20. Plus 11 is 31, plus 12 is 43, and so on. This number down here tells me that there are 69 competitors in total, which is exactly what you'd get if you were to add up all of those. This graph over here at the right, you see a number of points on it. Each point represents one of that column's data points. So for example, this blip right there, that's its x value, so to speak, is the upper bound of the finishing time, which in this case was 2 hours and 28 minutes, and there were 8 people finishing below 2 hours and 28 minutes. This data point here is for 2 hours and 34 minutes, and there are a total of 31 people below 2 hours and 34 minutes. So that has a y value of 31, and so on. So now the question's down below. If I wanted to estimate the median finishing time, okay, so half of 69, that's like 34 and a half. So I would have to find 34 and a half on my cumulative frequencies, on the y-axis. So 34 and a half, well, okay, the answer key is estimating that to be about 34 and a half. We go right to our graph. We go down to find an x value, and that would give us our median finish time. Whatever you want to estimate that as, it's a little bit less than 2 hours and 34 minutes. Sorry, a little bit greater than 2 hours and 34 minutes, maybe, but not too much greater, because 2 hours and 36 minutes is right here. So whatever you want to call that, I don't care. The number 2, the number of competitors who finished in less than 2 hours and 35 minutes. So I guess the book is assuming that the value we got for the last one is even less than 2 hours and 35 minutes, because they've got this dotted line right there, which they're using to estimate 2 hours and 35. They go up to the graph, and then they go over, and the estimate they've written down is that it should be 37. So they're estimating 37 competitors finishing in less than 2 hours 35. The percentage of competitors taking more than 2 hours and 39 minutes to finish. So again, we find 239, which we're going to estimate here. Go up to the graph, go left. That gives an estimate of 52. So how many are left? Well, there's 17 left. So 17 out of 69 would be finishing more than 2 hours and 39 minutes to finish. Whatever that is a percentage, go for it. And finally, Roman numeral 4, the time taken for someone who finished in the top 20% of runners. So we need to figure out 20%. Okay, so 20% of 69 is like 13.8. So we've got a line coming over here from 13.8. It goes down. Whatever time you want to estimate that as being. So something a little bit bigger than 2 hours and 30, but a little bit smaller than 2 hours and 32. So maybe 2 hours 31. And the top 20, the time taken for the top 20, that means we're looking for the value that is the 20th percentile. All right, so now that that's all done, and that was all just review, supposedly, now we can finally talk about section C, which is about standard deviation and variance. And I want to start off by telling you, don't read this page of the textbook. The first paragraph, this part's great. This is wonderful. The second paragraph was great. After that, this part here has a lot of wrong things in it. So just don't read this section. It's dense anyway, so most of you are not going to enjoy reading this page, and it just has things that are false in it. It's been corrected in later printings of the book, like online versions might have the correction, but if you have a hard copy, it just has errors here. So don't read it. Just skip straight ahead to the formulas, which are on the next page, where we have the variance and the standard deviation, and these formulas are also in the formula book. What does variance mean? Not a whole lot. I mean, in the same way that I could tell you that the square of the distance from Boston to London is about 27.7 million kilometers, and you'd say, well, that's great, but that's the square of the distance. Just tell me the actual distance. In the same way, I could tell you the variance of a data set, and then you should say, okay, wonderful, but just tell me the standard deviation, because that's more interesting and more useful to us. So the standard deviation, this bottom formula, what that represents is the average distance from the mean of all the data points in a given data set. Right? So you've got a data set. Most of those data values will not be equal to the mean. So most of them are going to have some difference between themselves and the mean. So the standard deviation is just the average of those differences. It's a pain in the butt to calculate by hand, as you can see here. What this formula tells us to do is we need to take each data point. So we'll take x sub I. Well, first we need to calculate the mean. So we got that value. Then we'll take the first data point, subtract the mean from it, square that. If this data point shows up multiple times, then we can multiply by its frequency count, divide by how many numbers there were in the data set. It is a huge pain in the butt to calculate by hand. We need to first calculate what the mean is. Then we take the difference between each data point. So we'll start with x sub 1, subtract the mean, square that value, multiply by x sub 1's frequency in case it appears multiple times. Then do the same thing for x sub 2 and x sub 3 and x sub 4 all the way to however many points we have. Divide this sum by how many data points there were, and then take the square root of whatever numerical value you have there. As you can imagine, this is very labor intensive. Thankfully, we can do this on the calculator pretty quickly, and I'll show you that in a moment. The variance is just the square of the standard deviation. So this first formula here is just the same thing as down below, except without the square root. And with a little bit of algebra, we can transform from this formula to this one, although, like I said, vast majority of the problems, we're going to use technology. But please do remember that these formulas are here, and you should know what each of the pieces mean just in case. All right, let's do some. Whoops, that's not the one we're doing yet. So here, we got Andrew and Brad. They're playing basketball. I've got the amount of points they both scored in the last 8 matches. I'm not going to do this entire problem, but let's just look at Andrew. I'm going to calculate the mean and the standard deviation for Andrew right now. Not by hand. I'm going to use a calculator. Here's how to do it. First thing, on a new screen, you're going to choose Lists and Spreadsheets. It's the thing that looks like Microsoft Excel. So you open that up. I've already done this, so I've already put in the data points in the first column. There's 8 of them because we had 8 games. I also named this column Andrew. I don't think that's actually necessary for this particular problem, but for some operations within lists and spreadsheets, you really want to have the column named. It also helps you keep track of what everything is, so I recommend naming the column. Next, we're going to calculate a whole bunch of stuff. Here we go. We're going to press Menu, as always. I want to do some statistics, so we'll choose that one. I'm going to do a calculation, and I'm going to do one variable statistics. It asks me, how many lists are we going to use? Well, only one list, this Andrew list. Okay. X1 list, that's asking me which list are we doing the calculations on. Currently, the A with the brackets next to it, that indicates column A, right? Because the columns are named just like in Excel, A, B, C, D, E, and so on. I could leave it like that if I wanted to, but I could also press to the right, and then I'll have the named column Andrew is there. This named column A is actually from another page that I have opened. That's not the same as A bracket. A bracket means column A. This means some other column that's named A from another problem I was working on earlier that we won't talk about. And this means column Andrew. So I'll choose that one. Frequency list, we'll leave it as 1 for now. I'll talk about that in a minute. Categories, I've never used those in my life, so please don't touch them. First result column, that means it's going to spit out the answers in column B. This is important because if I have other stuff in column B, then I probably want my results to go someplace else in the spreadsheet. But since column B is empty for me, this is all fine. I press OK, and here is everything. First thing I get is the average. This is X bar. I mentioned before that's the symbol for the mean of a sample. I know we're talking about the mean of a population because this is IB and everything's population, but the calculator uses X bar. We interpret that as mu. 25.5 is the average for Andrew. Done. Next one, not too interesting. This is the sum of all 8 of Andrew's data points. If we wanted to add them up, there they are. This next one is the sum of the squared values. So it's not 204 squared, but it is the square of each of those 8 data points added together. This is the big one. These two are the 2 different standard deviation values. The first one is for a sample. We're not going to use that in IB. We're going to use the second one. So it's the one labeled with a lowercase sigma. So Andrew's standard deviation is about 4.95. Below that, we're told there's 8 data points, and then we actually have the information for the 5-number summary. So we've got the min, first quartile, median, third quartile, maximum, and then the last one, I don't know why anyone would want this. 196 is looking there at the new thing that pops up when I highlight it. This is the sum of the squared values of each data point minus the mean. So it's like part of the formula for calculating the standard deviation. I guess in case that was relevant to your life, there it is. Anyway, the average is 25.5. The standard deviation is 4.95. The problem was then going to ask which of the 2 players is more consistent. So if I did the same thing for Brad, and I found out that he had a larger standard deviation, then I would say Andrew's more consistent because his data points on average were closer to the mean. If I found out that Brad has a smaller standard deviation, then Brad is more consistent. This next problem, this touches on a really important point, and it connects back to transformations of functions. So I really want to make a big deal about this one. Okay, we got a couple data points here. We're going to calculate the mean and the standard deviation the same way. Wonderful. Then I'm going to increase each data point by exactly 10. I'm going to find the new mean and standard deviation. We're going to see some things have changed in peculiar ways. And then I'm going to add something to this problem. I'm actually going to add in part D, I'm going to double each data point. And I'm going to do the same thing. I'm going to examine the new mean and the new standard deviation and see how they've changed. All right, so here I've entered in the 7 data points, and you can actually code these things just like in Excel. So the column B I labeled as column A just plus 10. You don't need to type it in with the A brackets. As you can see here in column C, as soon as I type the letter A, it just automatically comes in bold because it's interpreting this as the A. So it knows what I'm talking about. So 2 times A, press enter. It's asking now, is A a column or a variable? Because you might have had the value A stored somewhere else in the calculator to mean something. So I don't want that now. I want it to be a column reference, so I will press OK. And there we go. Now I've got all my information here. I now need to do a few different stat calculations. So I'm going to do my first one on, so I didn't name my columns here. So I need to I need to do this forcefully now. So I'm going to do, there we go. You can go in column E. That sounds great. Okay. Now over here, I'm going to do the same thing. Whoops. No, I wanted the stuff that was in column B. Wonderful. Whoop, cancel. I don't know what's happening. Okay. We're all good. And then I want to do it once more for column C. So a lesson to be learned from here, always name your columns. Okay, so I got stuff spread out not very nicely, but it's fine. Okay, so my first set of data had a mean of 69 and had a standard deviation of 6.04. Just remember those two numbers. 69, 6.0, excuse me, 6.05. Wow, embarrassing. 69 and 6.05. Then we added 10 to each data point. Let's see how those two values changed. The mean has increased by 10. The standard deviation has not changed at all. Interesting. Then we go back to the original data points. We multiply all of them by 2. Multiply them each by 2. Let's see how the mean and the standard deviation change. The mean has been multiplied by 2. The standard deviation has also been multiplied by 2. So why is this? So you can imagine those data points as just x values along a number line, right? And okay, so like we can calculate the average of them, we can calculate their standard deviation. Wonderful. If we add 10 to each of those data points, then that just means that they each move 10 units to the right along the x-axis. Clearly the mean has increased by 10. But the standard deviation should not have changed because they're just as spread out as they used to be. Whereas if we were to multiply them each by 2, and I don't have a fancy animation for this. That last animation wasn't even fancy. If we were to multiply them by 2, though, rather than all moving together, the distance from each to the origin is going to double. So the first one might go here, the second one might go here, the third one might go here, the fourth one's going to go out here, and so on and so on. So what's happening? They're getting more spread out. You see? So not only does their mean double, but also their standard deviation doubles too. And that's pretty important. Anytime that we add a constant value to every number in the data set, the mean is going to shift by that amount, but the standard deviation will not. And when we multiply by a set amount or divide, they'll both change. How would the variance change? Since the variance is the square of the standard deviation, if we doubled each point, then the variance would multiply by 4. Okay, how about this one? We've got a data set. 2 of the values are missing. We know the mean and we know the standard deviation. Can we find those 2 missing numbers? Yes, absolutely. It's going to come down to a system of equations. There's a lot of writing to this one, so I'm not going to write it all down. But if I shrink that down, we can actually see it. This is the work we'd have to do. The top part's pretty easy, right? We know that we've got 10 data points, so we add them all together, set it equal to 6. Move some stuff around, you get a plus b is equal to 14. That's fine. For the variance, okay, the variance is 3.2, which means that the standard deviation is going to be the square root of 3.2. So that's what we've got over here. And on the left, they're actually calculating out what the standard deviation is using the formula. So we've got a square root. We're dividing by 10 inside because there were 10 data points. And then each of these numbers that are being squared is the difference between each of the original data points and the mean. So the mean was 6. The difference between, so 3 minus 6 is negative 3. 9 minus 6 is 3. 5 minus 6, that's my negative 1 and another negative 1. Didn't bother writing the 0, that's okay. 4 minus 6, that's our negative 2. And a minus 6, there it is. So that's what's going on underneath there. So here's one where you have to use the formula book to work this out. But beyond that, it's okay. It's a lot of steps, but it's really just, it's a system of equations with a and b. So it's not really that exciting. But anyway, there it is. After that, the book finally gets to the formulas as they appear in the formula book. So the formula book, just like with the mean formula, the standard deviation formula that the formula book gives you has frequency values in it. That's okay. That's more generally useful than without it. So let's just do 2 more, and then this video will finally be done. So first, this one here. So now, remember before we had a frequency list on the calculator, and I said we were going to ignore it. Well, now I'm going to show you how to use it. So here I've entered in the ages in the first column and the frequency of the ages in the right-hand column. By the way, one thing I could have done instead of using frequencies, I could have just entered the number 11 twice. I could have entered the number 13 4 times, 14 5 times, and so on. And then we could have done this the exact same way as we did before, but this is a little bit less writing and a little less typing or whatever. So here we go. We're going to do the same thing as earlier. One variable statistics, still one list. I'm still going to use column A as my X list, but now my frequency list, the number 1 there just means that there's one count for each of the data points in column A. I'm going to use, I've got a lot of stuff programmed in here. I named it FREQ for frequency. That will be my frequency list. And now I want to put my results. I don't really want them to be in column B because that's where my frequency list is. So I'll put them in column C. And that is a column reference. Yeah, we're all good. Okay, here we go. The mean age is 14.48, and the standard deviation of ages is 1.75. Finally, last one. Here we've got the wages of a number of workers, of 200 workers at a particular company, and we want to estimate the mean and the standard deviation for here. So what did we do last time when we had to estimate based on grouped data like this? Well, we use the midpoints. So we do the exact same thing here. We'd find the midpoint of 360 to 369.99. Oh, come on, guys. This is annoying. I'm not going to do it. So we find the midpoint of each of these different groups. We know the frequency of each of them. We can calculate the mean and the standard deviation just using those as the actual data points. Again, that's just the best we can do. All right, so that's the end of chapter 23. Okay, I know this video was a long one. The most important thing here is to know how to do some really basic stuff on the calculator, to know where the formulas are in the formula book, and how to read the ones that we've talked about so far. All of these concepts are going to get thrown into high gear in the future sections, chapters 25 and 26 in particular. Chapter 24 is going to be just probability, so we won't really be talking about too much of this chapter there, but when we get to 25 and 26, we'll be using these concepts all in much more complicated scenarios. So my goal here is for you to understand and really appreciate statistics as much as the IB treatment of statistics will allow it. I don't want you to be one of those people who thinks that statistics is boring or stupid or not real math. People like to make jokes at statisticians' expense, like a statistician had his feet in an oven and his head in a refrigerator, and he said, on the average, I feel comfortable. That's a joke that's in the textbook. Another classic one is two statisticians are out hunting together. They both shoot at the target. One misses to the left, the other misses to the right, and they high-five each other and say, great shots, we got it. Haha, funny stuff, but stats is really beautiful. It is one of my favorite areas of mathematics. And for those of you who are taking or have taken in the past AP statistics, I hope that you had a wonderful experience there, because honestly, some of my most fond memories of a teacher were from teaching that course. And it does really pain me to know that IB Stats just doesn't quite live up to it. But we're going to do the best we can. So, okay, I've rambled enough. This video is over.